Thermodynamics. That's what we have for you. If you have not subscribed to this channel, endeavor to subscribe. Subscription is free. We are going to treat everything pertaining to thermodynamics in this channel, from the elementary to the last. You have past questions and the answer. Even when exam is at hand, everything is here. So if you follow us gradually, you are to what? Get everything you needed for what? Thermodynamics in this channel. So let's go to what we have. Said thermodynamics is the study of energy changes that occur in chemical and physical process. We said thermodynamics is the study of energy changes that occur in chemical and physical process. It is based on experimental facts on properties of matter in the bulk and does not contain time as a variable. When I see, what do we see there? We say that thermodynamics does not contain time as what? Its what? Variable. And thermodynamics is the gospel of Christ. The gospel of thermodynamics is gospel of Christ. He said, come as you are, you will never remain the same. Thermodynamics is all about internal energy, what you came with. And when you came, you are not going to remain the same when you are going back. And that's the gospel of what? Christ. We say thermodynamics is a study of energy changes that occur in a chemical and a physical process. That means it's all about matter, the state of matter, and the state of matter after a certain what? Time. We now say that thermodynamics does not depend on time. He has no time interval. Just like what God does. God does not depend on time. He has a time limit. He can do anything at any time. So we now said that it based on, we said thermodynamics is based on what? On experimental facts, on properties of what? Matter in the bulk, and what does not contain time as a variable. We now come into three basic laws of thermodynamics. Thermodynamics have three basic laws. And the first law is all about energy consumption. Energy what? Conservation. That is first law of thermodynamics. And that first law says, look at it, we say first law is concerned with the equivalence of different forms of energy. The first law is concerned with the equivalence of different forms of what? Energy. That's the energy change from this one to this one, the equivalent of it, without what? Any loss. Now look at first law. First law now say, first law states, look at it, first law states that energy, what is energy? First law states that energy, what is energy? Which we say, which may be, look at what energy we're talking about, which may be potential energy, or kinetic energy, or thermal energy, or electrical energy, or chemical energy, etc. We have many energy. We have solar energy. So we said, the first law states that energy, for instance, what's that energy? Which may be potential energy, kinetic energy, thermal energy, electrical energy, chemical energy, etc. in bracket, can be transformed from one form to another, but can neither be created nor destroyed. That means energy cannot be what? Created or what? Destroyed. That's the first word, law of thermodynamics. He's talking about what? Energy conservation. Look at it, he said, first law said that energy can be destroyed, can be transformed from where? Can be transformed from one form to what? Another. But can neither be what? Created nor what? Destroyed. He said energy can be what? Transformed from one form, that from what? Either potential energy to kinetic energy, or thermal energy to electrical energy, or electrical energy to chemical energy. So it can be transformed from one form to what? Another. But it can never be what? Created nor what? Destroyed. That's what first thermodynamics law is talking about. And we said that is total energy of a system and its surrounding must remain constant. Total energy of what? A system and its surrounding must be what? Remain what? Constant. Although it may be changed from one form to what? Another. We say that total energy must be what? Be conserved. Even though that energy will be changed from what? Heat to what? Maybe from what? Mechanical to what? Chemical energy. But in that process, there will not be any loss of energy. There will not be any gain of energy. And that energy will be what? Conserved. We said that is total energy of a system and its surrounding must remain constant. Although it may be changed from one form to what? Another. We now come to say that's what it means, conservation of what? Energy. Mathematically, we say the U, what's the U? We use U as internal what? Energy. And they may use E as internal energy. But I decided to use what? U as what? Internal energy. Why this become what? Infinite change in what? Heat. This Q stands for what? Heat. Infinite change in heat minus infinite change in work done. W means what? Work done. That means change in what? Internal energy is equal to infinite change in what? Heat supply or absorb minus what? Infinite change in what? Work done. For what do we say? For what? Infinitesimal. We will call it what? For infinitesimal. Infinitesimal. This stands for infinitesimal. This is infinitesimal. When I say where du is small change in the what? Internal energy. While infinitex q is the small quantity of heat absorbed. Small quantity of heat absorbed. And the infinitex w is the small amount of external work done at what? The same time by the system. The same amount of what? External work done by the what? The same time by the what? System. Note the symbol D and the what? Infinitex denote exact and inexact differential. What do you mean by exact and inexact differential? This man cannot be ascertained. Why? Because heat is a what? What we call part function. Heat is a what? Part function. While work is also part function. So you can't be able to get exact value of heat, because if heat is conducted to a particular part, there must be some of the heat being used to do a work. It will be radiated in a different form. So we cannot get exact value of what? Heat. That's what we call inexact. Then this man also work is also what? Part function, which we cannot get exact value of it. But the U, we can get what? It what? Exact what? Value. And what we say that D and this man is the exact differential, and this man is the what? Inexact what? Differential. That means when we differentiate this man, we cannot get exactly, some part will be lost. So when I say, what do we mean by what? External work. Look at my body. My body is a system. As I stand talking now, my body either giving heat to the environment and taking cold from the environment. That means work has been done by my body by giving heat to this environment. That my system, which is my body, my system have done external work to the body, while the environment have done what? Work to my what? System by giving me cold, and I'm giving them what? Heat. And that's what we say that this is the what? This infinite change in W is work. We call it what? Amount of what? External work done at what? The same time by the what? System. As you are giving the system cold, the system is giving the external what? Heat. Therefore, the system is doing work to the what? The environment, and the environment is also doing work, supplying heat or cold to the what? System. And that's what we say. That's the minus this Change, if you take change in Y and Q minus if you take change in what? W can be changed in internal energy. Let us go to what? Finite change in internal energy. For finite change, we said change in U, which is internal energy, minus heat is equals to heat minus W. Change in internal energy equals to what? Heat minus what? Work done. That's the work done to the external. So we said that is this mark, which is what? Change in what? Internal energy of the system must equal the energy absorbed from the system. Energy absorbed from the system. Look at it. This is change in internal energy, which is, I'm going to explain it properly. Let us understand. This means what? Change in what? This means change in internal what? Energy of the system must equal the energy absorbed from the system in the form of heat minus the energy lost to the surrounding in the form of external work done by the system. What are we talking about? Look at this explanation. Look at it. I came into this particular studio now. My temperature was hot as I came to this studio. What happened? I will begin to give heat to the environment. If somebody is close to me now, it will be feeling radiation of heat. While my body, which is the system, will be what? Taking cold, which you now see that the heat I'm giving out to the surrounding have done a work, which we call external work. Then the surrounding have done also work to me, which giving me the cold, which is in form of heat as well. We now say, look at it. Say that is this change in my what? Body now. We now begin to feel a change. Maybe as I'm hot, come here, and here is somehow cold. What happened? I'll begin to what? Exchange, giving the what? The surrounding, the what? The heat, the hotness, and I'll be buying the cold. At a point, both the surrounding and my system will have the same temperature, which we'll call at equilibrium temperature. I get what I'm saying. The time I came in, my temperature was higher than the temperature of the environment. I begin to send the hotness to the environment. While the environment had been doing work to me by giving me what? Cool. Then I begin to do work to the what? External, which is what? The environment, by giving the environment hot. So this is what we are saying here, that this is a change in internal energy in the what? Internal what? Energy of the system must equal the energy absorbed from the what? Surrounding. I absorb cold from the surrounding, which is what? Energy. In the form of what? Heat. In form of heat, I absorb it. Minus what? The energy lost to the what? Surrounding in the form of external work done by the system. I lost energy to the what? Surrounding, which is what? Heat. Then what happened? That heat I lost to the surrounding will be used to do work as a what? External what? Energy, which it is. Then why this one is the one I absorb? I came and I absorb. My system changed. And that's what we call change in the what? Internal energy. Which Christ, the gospel of Christ said, you will never remain the same. As far as you change your position to come close to him, you will never remain what? The same. You must have a change in you. As far as you come closer to Christ, you must have what? A change in you. And that's what we are talking about. That's the gospel of thermodynamics, that you will never remain the same. That your internal energy must have what? A change. Then when I come back to say, note that the first law does not hold when mass energy conversion is involved, as in a nuclear reaction. This first law terminates when we begin to talk about nuclear reaction. Nuclear reaction where the mass will be converted into what? Energy. Then this first law ceases to hold on that process. When I come to second law. Second law of thermodynamics is what? Concerned with the what? Direction of chemical change and the what? condition of what? Equilibrium. Why the first law did not be able to give us the direction. First law just tell us that energy can be converted from one form to other, but it doesn't tell us the direction of conversion. It doesn't tell us whether the conversion is what in a dynamics or whatever. But what it told us that energy can be shifted from this form to another. But the second law is telling us the direction, indicating the direction and also the rate. We say the second law is concerned with the what direction of the what chemical change and the what condition of what equilibrium. It determines the direction of what process, which determines the direction of process. It enables the prediction of the what direction of the natural and the spontaneous process. Look at what it does. It determines the direction of what process. That's the second law, determine the direction of process. It enables us predict of the what direction of the natural and spontaneous what process. Spontaneous process is the process that what occur on its own. He kick off on his own. Nobody what energizes. He just starts on his own. That's what the spontaneous process. We are going to see. Look at spontaneous process. Are those processes which takes place of their own what? Accord. Spontaneous processes are those processes which takes place of their own accord. On their own accord, they just take place. What are they? They are irreversible in nature. They are irreversible in nature. Can what? Immediately, just like our life is a spontaneous what reaction. Immediately you lose your life, you cannot recover it anymore. It's a spontaneous what reaction. On its own, it started. God just bring you out. You don't know how it started. You begin to what exist as a person, as a human being. But immediately something happened to terminate that life, you can never regain it again. So your life is what? Irreversible. And is a what? Spontaneous what? Reaction or spontaneous process. We say spontaneous process are those processes which takes place of their what? Own accord. They are irreversible in nature. Examples. Look at it. Examples. This means examples. Water runs down here. You see water running down here. It's a spontaneous water reaction. It's just on its own running down. Heat flows from hotter body to cooler body. Spontaneously. Heat will move. If I'm hot now, this hand is hot, this one is cool. If I put them together, you see the hotness will be transferring to this one. While this one will be transferring cold to my body. If somebody bath now, come out and what? Hold you, and your body is hot, maybe you have a malaria, and somebody bath, come out from bathroom and what? Hold you. What will happen? Your body now, which is hot, will be selling cold, will selling that hotness to the person that came out from what? Bathroom, while the person from bathroom will be selling cold to your body. At a point, two of you will come to an equilibrium. Nobody will be feeling each other again. Before you are feeling cold, while this person is feeling hot. At a point, you will come to equilibrium what? Temperature. Nobody will be feeling each other again. We'll call it what? Dynamic equilibrium of what? Two of the body. We said, again, what is again? As a body, again, a gas. A gas diffuses from a higher pressure to what? A lower pressure. Lower what? Point. That's the spontaneous what? Process. And this is an example of spontaneous process. In this, we have nobody by spontaneous process and second law of thermodynamics. Look at the second law of thermodynamics and look at the word spontaneous word process. Let us see what we call what? Non-spontaneous process and the statement of what? Second law of what? Thermodynamics. Non-spontaneous process. Non-spontaneous process are those processes which can be made to occur only by supplying energy from outside the system. Only by supplying what? Energy from outside the system. Examples. Energy is required to pump water uphill. If you want to pump your GP tank, you needed the energy to pump the water uphill. That means it's not a spontaneous. It's what? Is a non-spontaneous process. And to transfer heat from a cold reservoir to a hot one, as in the refrigerator. If you want to transfer heat from a cold reservoir to a hot one, you needed a what? Energy to push it. Then after that, we'll come into statement of what? Second law of thermodynamics. Statement of second law of thermodynamics. That is limitation of what? Second law of thermodynamics. It says number one, it is impossible to use a cyclic process to transfer heat from a hot reservoir and convert it into work without at the same time transferring a certain amount of heat from a hotter to a cooler what? Body, as in the heat engine, which we call turbine. We said it is impossible to use a cyclic what? Process. A cyclic process means a process that what? Move like what? When you go to train make use of what? Heat engine. So a cool one will be born. When the cold water is born, it's transferred to heat, which what? Heat turbine, and the heat turbine will what? Transfer it into what? Mechanical work. So when I said it is impossible to use a cycling process to transfer heat from a heat reservoir and convert it into work without at the same time transferring a certain amount of the heat from a hotter to a cooler body, as in the heat engine. Look at it. If I'm transferring what? Heat from what? A tank now to what? The chamber of what? Turbine. There must in tendency that part of this heat will be lost. It's not okay that I can transfer the whole heat as heat is now. I transfer the whole heat without anyone lost. It's not possible. That's the second law is telling us. That it's not possible to transfer heat from a reservoir or any particular place to another place without what? Loss. Without that heat doing work or one or two things. He must have a miscellaneous what? Heat loss. So that's what he's saying. He said it is impossible to use a cycling process to what? Transfer heat from what? A heat reservoir and convert it into work without at the same time transferring a certain amount of heat from a hotter to what? A cooler what? Body, as in the what? Heat engine. Number two statement. It is impossible to use a cyclic process. A cyclic process is the one that what? He goes and come back. He goes cyclics. I don't say that. It's impossible to use a cyclic process to transfer heat from a cooler to what? A hotter body without at the same time converting a certain amount of work into heat, as in the heat pump. There's no way a heat can be transferred totality. Do you understand that? There's no way heat can be transferred totality. There must be a loss. That's what the man is saying. In a what? Cycling process, which we call it what? In a pump engine, that's a heat pump, where we use what? A pump to pump what? Heat to the what? Ignition. You know, train make use of heat to what? Move. It's not using fuel. It's what? Using heat combustion to what? Operate. So in that train, that way we have what we call cycling process of transferring what? Heat. When we come to II, we have mechanical work can be completely converted into heat. Look at it. Look at mechanical work. If you rub your two hands now, you will see that mechanical work have been converted into what? Heat. So the whole work you have done with your mechanical movement will be transferred into heat. But the whole heat cannot be transferred into what? Mechanical work. What it? Mechanical work can be completely converted into heat. But on the contrary, heat cannot be completely converted into work without making other changes, either into the system or the surrounding in a cycling work process. Just as an example, if you rub your hand, you will see the more you apply the force, the more the heat. You will now turn the whole mechanical into heat. But there's no way those heat you converted can be converted back to what? Mechanical, without some of it being lost. That's what this man is talking about in third statement. In the first statement, he said that what you want to transfer the whole heat using a cycling process to transfer the whole heat to another chamber. There must be what? Some miscellaneous. It cannot be totality. That's what he also say here. It's impossible to use it in a cycling process. And that's what we call statement of second law of thermodynamics. It's always there to be asked. you should state the statement of what? Second law of what? Thermodynamics. Look at his word statement. Then we are now going into what we call thermodynamics terms. Third law of thermodynamics attempts to evaluate thermodynamics parameter. Now let us look at the third law. Third law states that every substance has a finite positive. Every substance has a finite what? Positive entropy, but at 0 Kelvin, the entropy may become 0, and does so because in the case of a perfectly crystalline substance. Can we go back? I said third law states that every substance has a finite positive entropy, but at 0 Kelvin, the entropy may become 0. That's 0, may become 0. And does so because in the case of a perfectly crystalline substance. That's the third law. The importance of third law is that it permits the calculation of absolute values of entropy of pure substance from thermal data alone. We said the importance of third law of thermodynamics is that it permits the calculation of absolute values of entropy of pure substance from thermal data alone. We now come to what? Thermodynamics terms. We said number one, system. What do we call system? My body is a system. We said myself is a system. You watching this video, you are a system. We say system. A thermodynamic system is that particular part of the universe, which we call physical universe. And what's that physical universe? Matter. We're talking about matter. Look at me. It's a matter that we are interested in and wish to what? Study. We said system. A thermodynamic system is that particular part of the what? Physical universe. What's the particular part of the physical universe? We call it what? Matter that we are interested in and wish to what? Study. And I am the example of a system which is matter. Then we'll come to boundary. Boundary is a separation between the system and the surrounding. Look at me. If you look at me, inside me is a system. While my body, this flesh, is what we call wall, which we call boundary. That's the boundary or wall that prevents the system which is inside me, which is my system. Just like a pure water. Pure water. Water is inside the bag. Why the bag become the boundary? The bag that holds the pure water is boundary. Why the water inside become the system? We say boundary. There is the separation between the system and the surrounding. Look at what separates me from the surrounding. This is my flesh. Separate my system, which is my body, with my surrounding. Look at the surrounding. Then we'll come to surrounding. Surrounding is any system which can interchange energy with a given system. Surrounding is any system. You know that surrounding itself is a system, because surrounding is a producing heat. Just like when I come inside this studio now, the studio is very, very cold. So it's selling cold to me, while my body is selling heat. So the surrounding, which is the studio environment, is also a system. We say surrounding is any system which can interchange energy with a given system. So myself is a system. The surrounding that around me is a system which is selling and buying. I sell, he buy, he sell to me. That's what he said. Any system which can interchange energy with a system. Full stop. A system can interchange energy with its surrounding by the performance of mechanical work or by a flow of heat. If I'm doing mechanical work now, what will happen? Or as I am now, I'm sweating, and what will happen? I'll be selling heat to the surrounding. the surrounding will be selling cold. At a point, this place will be what? At equilibrium with my body. So the surrounding is a system, my body is a system. So we communicate. Two systems communicate. And that's what we are talking about. Surrounding is any system which can interchange. You must be interchanged. If surrounding is not interchanged, it's no more a system. So for a surrounding to be a system, you must interchange, that you must buy or sell. Either the surrounding is selling cold to you, or you are selling hot to the surrounding, or the surrounding is selling what? Hot, and you are selling cold to the surrounding. There must be buying and selling, which is exchange of what? Heat. And we said is any system which can interchange energy. What's the energy? Heat. When we say energy, we are talking about what? Heat. Heat. Which can interchange what? Heat with a what? A given system. Or we said a system can be interchange energy, which is what? Heat. Interchange what? Heat. When we say energy, we are talking about heat with its surrounding by the performance of what? Mechanical work, or by what? A flow of heat. That by mechanical work, if I'm not rubbing myself, I'll be generating what? Heat. That mechanical work I'm doing, I'll be converted into heat. That's where you are stressing yourself. What will happen? Heat will be coming out from your body, because your mechanical work we are performing have been converted into what? Heat. So we now see what we mean by what? The surrounding, the boundary, and the word system. These will be used when we come into calculation. So you have to know that the system, a thermodynamic system, is that particular part of the what? Physical universe, which we call what? Matter, that we are interested in what? To study. And the boundary is the separation between the system and the what? Surrounding. This is my boundary. Look, my world is my boundary. Then my surrounding is a system which is around me, which can buy from me, or I buy from him, or we exchange to each other. That's what we call what? A surrounding. Let us see in the class, the next class, which is called class 2. This is the first class. And if you have not subscribed to this channel, endeavor to subscribe. This is a standard that you what? Get your A and B's. If you rely on this channel when we come into calculation, you'll be able to know the proof that is in the what? Thermodynamics and the what? Electricity and magnetism that is involved. Thank you for subscribing. Thank you for commenting. Thank you for sharing this what? This channel. See you in class 2.